In this video, we're going to look at the maximum value function, the envelope theorem, and duality. Recall how we defined the envelope theorem from the previous video. The partial derivative of the indirect objective function with respect to a parameter equals the partial derivative of the direct objective function with respect to the same parameter but evaluated at the optimum. The direct objective function only has the unoptimized values of the choice variables as independent parameters. The indirect objective function is a function of the equilibrium values of the choice variables, which are themselves functions of the parameters. Parameters enter indirectly. When we take the partial derivative of the indirect objective function with respect to a parameter, choice variables adjust to their new optimum values. Following Dixit in Chapter 5, we're going to let theta refer to parameters such as price, budget, etc. Then our constrained optimization problem will look like this. Maximize f of x and theta subject to g of x equals c. Now the theta refers to parameters such as prices or the particular parameters of a utility function, whereas here we don't have any parameters. For example, we won't have prices or something along that line, but of course we can put a theta in there as well, which we'll do when we generalize this particular approach. So we construct the Lagrangian as a function of x, lambda, and theta, which is equal to the objective function f of x theta minus lambda c minus g of x. The first order conditions tell us that the first derivatives with respect to any of the x's is equal to 0, and the first derivative with respect to lambda is equal to 0, and those are evaluated then at the optimums, where the x star refers to the vector of optimum values of x. Of x1, x2, etc. We get the maximum value function, which we denote by a capital V, by substituting x star into the objective function f. So then our maximum value function looks like this as a function of x star and theta. A first Taylor series approximation is obtained by taking the total derivative of v, which is equal to f x star plus d x star, a small amount of x star, and theta plus a small amount of theta, d theta, minus fx star theta. So the difference between the function evaluated at a very small change in x star and in theta minus the original function is equal to any little change in the value of the value function. So we can then rewrite this as the partial of the objective function with respect to x times dx star plus the partial of the objective function with respect to theta times d theta. From the first order conditions, we know that f sub x, so the first derivative of the objective function with respect to any x, is equal to lambda times the first derivative of the constraint with respect to x. And we found before that this lambda is equal to f of x over g of x, where these subscripts refer to the derivatives. Substituting that in, we get the result that the little change in v, dv, is equal to lambda partial of g with respect to x times dx star plus f theta, where partial of the objective function with respect to theta times d theta. But because the g of x is equal to the partial of c with respect to x, and c is a constant, all right, up here c is simply a constant, therefore it's equal to 0, and therefore this term here is 0, and we get this result that the partial of f with respect to theta, d theta, is equal to the change in the value function. How do we interpret this? Well, to calculate the effect of a small change in a parameter theta, we only need to evaluate the expression at the initial optimum choice, x star. So remember, with the Taylor series expansion, it's about a particular point, and the point we choose is this optimum point, x star. Now suppose the above problem is to minimize cost. Well, if we do that, and we specify cost as, say, theta x, where theta might be prices, so we might have, these are input prices then, we want to reduce or minimize the input cost, so we'd want to minimize the input price of x1 times x1 plus the input price of x2 times x2 and so on, but we want to express that as a maximum, so in order to do the maximization, we add that negative sign here. And again, we have the same constraint set over here as g of x equals c. Then we take a small negative difference in the value function, maximum value function, is equal to d theta times the original objective function, which is this one here. So that gives us minus d theta x star when we take the derivative here with respect to the total derivative with respect to theta. And we then get that the small change in the value function is equal to a small change in the parameter times x star. So V is the minimum cost of producing output C for input prices theta. Now the envelope theorem application is as follows. Suppose we have two situations. We have an optimum if the parameter values are theta 1. Our optimum is x star with this superscript 1 to the left, and it's x star with superscript to the left 2 if theta is theta 2. So the maximum value function is the same. V of theta equals f x of theta and theta. So this part here, V of theta and f with the optimum x1 of theta coincides, so V, the maximum value function, and the objective function coincide at theta 1. If the theta 2 is our parameter set, then we get x2 star being our optimum, and then the maximum value function of theta is equal to the objective function at theta, and at x2 star, they coincide at theta 2. So we can see that diagrammatically here, where we have theta and our x1 star and our x2 star, resulting in two different functions, objective functions, as theta were to change, and they intersect, or pardon me, are tangent to this value function, maximum value functions at theta 1 and theta 2. And you can see that these are basically envelopes. So this V of theta is an envelope of all of these different objective function values based on what the optimum is. So if the optimum is x1 star, then at this particular point right here, it's equal to the value function. But as theta changes, you'd want to change this x star from x1 to x2 if you shift from theta 1 to theta 2. If you don't, you end up here rather than up here. So the optimum value function is the upper envelope of the family of value functions in each of which the choice variables are held fixed. So the choice variables are held fixed here, and we see that by the x1 star and the x2 star, but they're allowed to change along this v theta function. The f x theta functions are concave, and the v of theta function is convex. For cost minimization, we get the following diagram. So here are our parameters. Here's our cost. Now we have a minimum cost, which is a concave function, and that's the envelope for each of these cost lines for a fixed value of x. So this line represents a fixed value of x, and there it is tangent to the minimum cost at that point here. So if we change, for example, prices of inputs, and we maintain this x value here, then we see that we deviate from the minimum cost as the theta changes without us changing the value or the choice variable x. Now notice that the cost lines, while they're linear, they're really quasi-convex. So again, we get these tangencies of a concave function to a convex function. Now, as Dixit points out, there's a more general case where we have that these parameters appear in the objective function and in the constraint function, which we didn't have before. So in that case, what we get is the partial of the constraint function, g, with respect to x, dx, plus the partial of the constraint function now with respect to this parameter theta, times d theta has to equal 0. Now, our earlier result gave us this here, where a small change in the maximum value function was equal to minus lambda g of theta d theta plus partial of f with respect to theta d theta, and we then get this result here. Now, what we did in the earlier result, of course, was this, because we did not have a theta at that point, this then went to 0, and we were left solely with this result down here. All right, so a change in d theta has a direct effect on increasing the value of g by g x star theta d theta. We don't change the x star. This acts exactly like an equal reduction in c. The equivalent reduction in c reduces v by this amount here, lambda times the partial of the constraint function with respect to theta times d theta. Notice that previously, as I mentioned, that this was the result we had. Now we have that we've added this to it because we have this theta in the g constraint function. So we get minus lambda g partial derivative of the constraint function with respect to theta times d theta plus the partial of the objective function with respect to theta times d theta. Now, if we were to take this a bit further yet and separate changes in the c, the right-hand side of that constraint set, from theta, so in other words, we don't lump the c in with the theta, then we get the following result, which is the same as the result up here, this first part, and then we have to add this lambda dc in it. Now, we want to go a little bit further and consider the use of the envelope theorem in consumer demand theory. So by definition, the indirect utility function is always the maximum utility, so it will be greater than the value of the Lagrangians as shown to the left. All right, so here we have the same result we showed above, but instead of having this indirect utility function here on the vertical axes and m on the horizontal axes, we had v as the value function, the maximum value function on the vertical, and we had theta on the horizontal axis. So here we have the case where we're maximizing utility as a function of Q1, Q2, subject to this constraint set that P1, Q1 plus P2, Q2 has to be equal to M. Now, we refer to it as the envelope theorem because the indirect objective function can be viewed as the envelope of all points where the direct objective function is evaluated at optimum values of the choice variables. If our budget changes, so do Q1 star and Q2 star. The indirect utility function incorporates these new values, but the direct objective function does not, which results in the direct utility function, we're floating along this line, with the indirect, we're going along this line. All right, and it's all because the direct objective function does not allow for changes in the optimum choice of Q1 and Q2. So we're going to let this phi, capital Phi, denote the indirect utility function, and we have that the indirect utility function is a value of is a function of output price and budget, of the prices of the goods and the budget, and it's equal to the direct utility function at the point E above. At point E there, we have that the indirect utility function and the direct utility function are equal. So basically what we have is this here, where these Lagrangians, if you like, are or represent the direct utility function, and the omega star represents the maximum value function. So what about duality in economics? So we look at first the primal, and in an earlier video I showed that for U Q1 to the 3/4, Q2 to the 1/4, that we have Q1 star was 3m over 4p1, Q2 star was m over 4p2, and these were the Marshallian demands. Substituting those into the utility function gives the indirect utility function, which when we calculate everything through, we get this somewhat complicated expression where we have m over 4 times 3 over p1 to the power 3/4 and 1 over p2 times power to the power 1/4. Solving for the indirect utility function, or solving the indirect utility function for m, gives us that m, and we call this the expenditure function, is equal to 4 times the utility function, or just utility, times p1 over 3 to the 3/4 and p2 to the 1/4. This is the expenditure function, which is why we use an E here. Now, Roy's identity tells us that Qi, and we'll look at a proof of Roy's identity a little later on, any Qi is a function of prices, and m can be derived from the indirect utility function by taking the negative of the partial of the indirect utility function with respect to that price, to the price pi, divided by the partial of the indirect utility function with respect to income or budget. So for Q1, when we do that, we find that the partial with respect of the indirect utility function with respect to budget is given by this complicated expression, and this even more complicated expression for the partial of the indirect utility function with respect to P1. We divide the negative of P1 by the partial of the indirect utility function with respect to m, and when we solve this through, we get 3m over 4p1. Again, this is equal to the original, or to the ordinary demand function up here. So we get these demand functions, these Marshallian demand functions, back when we use Roy's identity. Now consider the dual to the above problem, to the above primal. So we want to now minimize our budget expenditures, P1 Q1 plus P2 Q2, subject to the constraint that the utility function is given by this, And normally we'd put a little zero or something on that utility function to indicate that it's a particular level, or that we want to be at on a particular indifference curve. So then we set up the Lagrangian as follows. We find the first derivatives with respect to Q1 and Q2, which we do here and here, set them equal to 0. That gives us theta, where confusingly I'm using theta here as a Lagrange multiplier, and up above I used it as for parameters. You'll just have to deal with that. And we find these results. We set the thetas, the right-hand sides equal to each other, so this side equal to this, and we solve for Q1, where Q1 is now a function of P2, P1, and Q2, and we then put that into the utility function. So we have it in here. This is that Q1, 3Q2, P2 over P1 to the power 3/4, which was originally Q1 to the power 3/4, but Q1 is equal to this here, and Q2 to the 1/4. That gives us this expression for U, which then turns out, when we solve for Q2, to give us the compensated, which is why I have a C there, the compensated demand function for Q2. We could do the same thing for Q1, and we get that Q1 is equal to U times 3P2 over P1 to the power 1/4. So we have the two Hicksian, or compensated, hence the subscript C, demand function. Qi, rather, denoted with the C, is a function of P1, P2, and U. Substituting the compensated demands into the objective function, a complicated expression that we then work through, and we then show that that's equal to 4 times P1 over 3 to the 3/4, P2 to the 1/4 times U, which is the expenditure function as a function of P1, P2, and U. And it's the same as above. So we solve the expenditure function for U, and when we do that, we get the indirect utility function back, and it's the same. If you look back a couple of pages, you see that it's the same as the indirect utility function we found above. So let's summarize this utility for the case of consumer demand theory. We had the primal, which was to maximize utility as a function of Q, subject to the budget constraint M equals P times Q, and these are vectors, so this is a row vector times a column vector. And the dual problem is to minimize that PQ, this P times Q, subject to a level of utility. When we solve the primal problem, we end up with the Marshallian demands, which are a function of price and income. And if we solve the dual problem of minimization, we get the Hicksian or compensated demand functions as a function of price, which is the same as here, except now we have it as a function of utility as opposed to budget. If we take the Marshallian demands, substitute them into the objective function, then we get the indirect utility function, which is a function of prices and income, and that's equal to U. We can solve for M from this expression here, and we get the expenditure function as a function of prices and utility equal to M. We could have got there the same way once we had the Hicksian demands. We could have solved that for putting these compensated demand curves back into the objective here, and we get that expenditure function, which we can solve for U to get the indirect utility function back. Now, if we stay on this side, on the primal side, we can take the indirect utility function, use Roy's identity, and then we get the ordinary demands back. Or on this side, we can take the expenditure function, use Shepard's lemma, and we get the compensated demand functions back. Just as a review then, Roy's identity is given by us the ordinary demand functions, Marshallian demand functions, as the negative of the partial of the indirect utility function with regards to a price, divided by the partial of the indirect utility function with respect to the budget. Shepard's lemma tells us that we can get the compensated demand functions as a function of price and utility by taking the first derivative, partial derivative of the expenditure function with respect to pi. Shepard's lemma will be considered in following lectures somewhat more, as will Roy's identity. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.